Hello, I'm Dr. J, and this is my guide to Venn diagrams. In the last couple of videos, we've been talking about the mathematical concepts of sets, subsets, set comparisons, and set operations. And in so doing, we primarily were using mathematical notation to describe what was going on. That is, we were using the curly braces, the funky-looking E symbol, the parentheses, square brackets, and that kind of thing. And so if you were a little bit confused about what was going on, or if that mathematical notation was new to you, then this video might help, where we're going to introduce the idea of Venn diagrams, which are a visual representation of sets. And hopefully once we have introduced this concept of Venn diagrams, then you can go back and you can look at the other videos and understand what was going on when we were talking about those subsets and set comparisons. As always, there's a link down below to a printout of the slides in case you want to print those out and take notes as we go. So Venn diagrams are represented visually, as I was mentioning, and we're going to start here with a rectangle. And this rectangle is denoted with the letter S, and if you remember from previous videos, the letter S represented our universal set. So this rectangle represents the universal set. And what I mean by that is that every element, in this case, we're going to be thinking about the elements as being points in this rectangle. So all the elements that we're going to consider are those elements that are points inside this rectangle. So we're not going to consider any points that are outside of that rectangle, which is why I've intentionally now grayed out the background. The grayed background is a visual indication that this is not sort of in play, if you will. So the only elements we're considering are elements that are inside this rectangle, that are the points inside the rectangle. Now let's add our first set. So here's a set. The set is indicated by a circle with the letter A. The A indicates the name for this set. So this is the set A. And all the points that are inside this circle, that is the points that are now orange, those points are in this set, whereas the points that are outside of that circle are not in the set. Okay, so that's one set. Now we could go further. We could add a second set. So here's now a second set. This is the set B, indicated by the circle here with the letter B. And now any points that are inside that circle are in the set B, and any points outside of that circle are not in the set B. And now things have gotten a little bit more interesting because we have an area here where these two circles overlap. So as a reminder, all the elements within the circle A are in the set A. And all the elements within the circle B are in the set B. But there are elements or points that are in both circles. It's sort of represented here by that football-shaped overlap. And that area indicates all the elements that are in both sets, that are in set A and in set B. We can go one step further and we can add a third set. Now we have a set C, and this set here is a greenish color. And all the elements that are inside that circle C are in the set C, and all the points or elements outside of that circle are not in the set C. But things have gotten even more complicated now, because now we have areas of overlap between A and B, as well as between B and C, and as well as between C and A. And those areas represent elements that are in, respectively, A and B, elements that are in both B and C, and elements that are in both C and A. Alright, now we also have a sort of a bulging triangle in the very center of these circles. And that bulging triangle represents elements or points that are in all three of those circular sets. They're in A, they're in B, and they're in C. And if you've seen Venn diagrams, or if you Google for Venn diagrams, this is the picture that you normally see. And so this picture is representing three different sets and the elements that are in that set. Now, there's no good reason why we had to choose circles. That's just the most common choice, but we could choose really any kind of polygon, right? So we could have done squares or triangles or, irregularly shaped polygons. All of those would be perfectly fine. It all just depends on what it is that we're trying to demonstrate. For the purpose of today, we're going to stick with the universal set being a rectangle, and we're going to stick with subsets of that universal set being circles. Alright, so that basically is an introduction to Venn diagrams and how we represent sets with Venn diagrams. Now let's get into the concepts that we had before about subsets and supersets. So here is that same universal set S, but now you have a new set D. That's this yellowish color. And again, all the points that are inside that circle that are currently yellow are part of or elements of the set D, and all the points outside that circle, which are currently white, are not elements of D. And now you might be thinking to yourself, hey, D is a subset of S. And yes, you got that right, and we're going to talk about that a bit later. But right now, we're going to introduce a new set. So here's a new set. It's a set F. In this set F, you'll notice here that all the elements that are in F are also elements in D. And you can see that clearly if I flip back. So here's D, right? And all the points that are currently yellow are elements of D. And if we go forward, now here are the points F, which are all also points and elements of D. And therefore, because all the elements of F are also elements of D, that means that F is a subset of the set D. Now you might also be noticing, hey, look, there's also area in D, or there's yellowish color that's still visible. And that yellowish color indicates points or elements that are in D, but that are not in F. And because there's at least one element in D, but that's not in F, then that tells us that F is actually a proper subset of the set D. And now we can reverse the idea here, and we can talk about supersets. So remember that supersets are somehow larger, right? Subsets are smaller and supersets are bigger. And so we can say, look, in F, all the elements that are in F are also elements in D. And therefore, D is a superset of F. But not only that, there are elements in D that are not elements in F. And therefore, D is a proper superset of F. So here we have a visual depiction of this idea of supersets and subsets. You'll notice in our previous diagram where we had the sets A, B, and C, none of those sets were subsets of each other because all had elements that were not in the other sets. Okay. All right, now we're going to move on to the second half of this video where we're going to talk about set operations. And for the discussion about set operations, we're going to be considering two sets, A and B, which are both subsets of our universal set S. Now, if you want to really practice, you should pause the video. Well, pause the video in a second when I give you the instructions. So here's the instructions. Go down to the description, print out the slides, print out this particular slide right here, maybe 10 times, and try on your own before you go ahead and try to determine what areas of this picture, go ahead and actually color them in. What areas of this picture correspond to, say, the union of A and B? What area corresponds to the intersection of A and B? What area corresponds to the set difference of A minus B or B minus A? What corresponds to the complement of A or the complement of B? You could also think about, all right, you have the union of A and B. What's the complement of that union? Right? So you could do all this by pausing the video right now. Hi, welcome back. I hope you're sitting there with your colorful pieces of paper where you've indicated the union of A and B, the intersection of A and B, A complement, set difference of A minus B, and so forth. The first operation that we introduced before is the union operator. And as a reminder, the union is composed of all the elements that are in one set and all the elements that are in the other set. So in this case, the union of A and B contain all the elements in A and the elements in B. So if we think about coloring this picture, we're going to think about first coloring the circle for A and then coloring in the circle for B. And that total area, which is both of those circles, is the union of A and B, as depicted here. The second operation that we talked about is the intersection operator. The intersection of a set A and a set B is the elements that are in A and in B. The area in these Venn diagrams that indicates that an element is in both of the sets is the areas where the two sets overlap. So in this case with the two circles, it's the football-shaped area where those two circles overlap. That's the intersection of A and B. The third operation we talked about is the set difference operator. And unlike the union and intersection operator, order does matter for set difference. So here we're first taking the set A minus the set B. And if you think about coloring this, what you want to do is you want to color in A, and then you want to erase that part of A that is also in B. And so if we colored in the full circle for A, and then we took an eraser and got rid of the area in B, well, that's just the intersection between A and B. So we erase that area, and what's left over, this partial moon, is the set difference of A minus B. And now just to visually show you that order does matter, we can do the opposite. We can take B minus A. where we first color in B, and then we erase the area that's also in A, which is again the intersection of A and B, and we have the result, which is this moon shape, but a different moon shape than the previous moon shape. We'll take a final example of a set difference. Here we took the universal set and we subtracted out the set A. So we colored in the whole area for the universal set, and then we erased the circle that represents set A. But we actually had a special name for this operator, or for this set. This set was called a complement. And as usual, when we're doing complements, the universal set is implied. And in this video, the universal set was always that big rectangle, and so that is the implied universal set. And so when we take A's complement, we color everything within that universal set, but that's not in A. Here's another example of a complement. This one is a little bit trickier because first you have to take the union of A and B. And if you flip back a couple of slides or go back in the video, you'll see that the union of A and B was just the area of both of those circles. And if we want to take the complement there in the universal set S, then we just color everything that's outside of both of the circles. Now, one of the things you could do is you could test yourself here and go back and look at De Morgan's laws. De Morgan's laws told us that this complement, that is A union B complement, that was equal to A complement intersection B complement. And so you could test yourself using these Venn diagrams, color them in, print out that slide again, and color in those different steps of De Morgan's laws just to prove to yourself that in fact it seems to be true. Alright, so today we use Venn diagrams to visually represent sets as well as subsets, set comparisons, and set operations of union, intersection, complement, and set difference. In the next slide set, we're going to introduce the idea of disjoint, mutually disjoint, and a partition. So, until next time, have a great one.